So this is a problem on truss, and this is by the transformation stiffness approach. We need to analyze the truss and find the forces in the members of the truss. So here we have three members in this truss, what is shown to us, and there is joint D at which all three members have been connected, and at other end at A, B, C they have been hinged at these points. So from this, we can come to know that the degree of kinematic indeterminacy of this truss, which is expressed as 2j minus r, each joint has 2 degrees of freedom minus the number of external reactions. So if we calculate from that, it will come to the degree of kinematic indeterminacy dk as 2 here. So the two unknown displacement that will exist here are delta 1 and delta 2, that is horizontal displacement and vertical displacements at joint D. Accordingly, we'll assign the coordinates. You can see the coordinates what I've chosen here is 1 is the coordinate in vertical direction, 2 is the coordinate in horizontal direction. So whether this direction will be upwards, downwards, it is at the freedom of the your wish. And even the direction of second coordinate can be chosen towards left also. So there's no problem in numbering and choosing the direction of these coordinates. You are free to choose any direction and any numbering of the coordinates, but the location of these coordinates will be at joint D here, where the two unknown displacement will exist. So unknown displacements have been taken as delta 1 and delta 2. Delta 1 correspond to vertical displacement of joint D. Delta 2 corresponds to the horizontal displacement of joint D. Now, this is the global coordinates what we have written here. And in case of truss, each member will have one displacement, either axial compression or elongation. That is when it is in tension. So there will be 1 degree of freedom along each member. So there will be one coordinate for each of the members. So here there are three members. So we'll come across three elemental coordinates here from 1 star to 3 star. These are the three elemental coordinates what will be there along the members. And the member properties have been listed in this problem, that is AE value is given here and L value has been expressed here for each of the members. Now first, if we write the force matrices, we'll come across two force matrices here, that is P and PL matrix. P matrix represents the forces which are directly applied in the coordinate. If there are any forces which are directly applied in our coordinate, then all those forces will be taken into P matrix. Now in this case, at joint D, we have two coordinates and also there is a vertical downward force acting at joint D. Now this vertically downward force will be taken in our P matrix. So I have first coordinate over here in vertical direction and 80 kilonewton force is applied in this vertical direction. Note that the direction of the applied force and the direction of the coordinates are same. The force is applied in the direction of the first coordinate. So that will be 80. That will be the first element of this P matrix. In the second coordinate direction or in the second coordinate, there is no force which is present over here at T. So this will be 0. So our P matrix will be 80, 0. And the PL matrix, what happens is the PL matrix represents the forces which are applied other than the coordinates. If any forces are present other than our coordinates, then all those taken will be taken care in PL matrix. So in case of trusses, there will be no forces which are applied over the member other than the coordinates, means I mean by forces which are acting over the member. So no such forces will be present in the trusses. The forces will be applied at the joints in case of truss. So we come across no force which are acting on the members. So this PL matrix in case of trusses will remain a zero matrix. So that will be PL will be 0, 0. So all the elements of this PL matrix will be 0. So that will be the two force matrix what we have to write here. Now after this, coming to the element stiffness matrix. Now for each of the elements we'll write the stiffness matrix. In trusses, for each element the stiffness matrix is expressed as A by L. So if I consider the first member here, it's A and E, that is first member is AD, A and E that product A and L has been expressed here. So both are 400. So if I take the ratio A by L, it comes out as 1 Newton per mm. Okay, so that will be 1 Newton per mm over here. And the next one, what you have is, similarly, if I take A by L ratio for the member BD, which is our second member, it also comes out as 1. And similarly for third member, 800 by 800, it will be 1. So that all the three element stiffness matrices will come out to be 1 here. Okay, so these will be arranged in the unassembled elements global stiffness matrix. So all these elemental stiffness matrix will be arranged along the principal diagonal of this unassembled global stiffness matrix. Rest other elements will be zeros. So if I put them over here, it will be a diagonal matrix 1 1 1, like what is shown over here. Now this, what we need to do is to convert this into global stiffness matrix. To convert it to global stiffness matrix, we require the matrix what we call the displacement transformation matrix over here. So here is the displacement transformation matrix. For developing the displacement transformation matrix, what you have to do is you need to start applying the unit force in the global coordinate and unit displacement in the global coordinate, and determine what are the displacement in the elemental coordinates. So I'll take the first coordinate, apply unit displacement in first global coordinate, find what displacement are developed in the elemental coordinates which are along my members. Similarly, I'll go for the second global coordinate and apply unit displacement over there, and then go for determining what forces are developed in the elemental coordinates. That is how you develop the displacement transformation matrix. Now coming to the first column of the displacement transformation matrix, what I need to do is apply unit displacement along the first global coordinate, what is here. So 1 mm or 1 unit displacement has been applied in vertical direction at joint D. Now to find what are the displacement along the elemental coordinate, I'll have to measure the displacement along these three members. So first member AD is perpendicular to this applied displacement. There will not be any displacement which will be coming in the first elemental coordinates. So D1 star 1 will remain 0. Now for the second one, just take this triangle, drop it perpendicular from this point onto the member. So in this component, this DD2 represents the displacement along the member BD, which is required for us. This is actually the displacement what is taking place along the elemental coordinate when 1 unit displacement is given in the global coordinate. So if I find out this DD2, that will be my D2 star 1. So this is nothing but 1 into cos of 60 degree. Either you can express with your sine or cos, that is left to you. Taking here, what I have taken is minus 1 into cos 60. This negative sign is taken because the member length is shortening. So for that purpose, negative sign has been assigned over here. If the member length is reducing or it is getting shortened, so negative sign will be assigned for that. So DD2. Similarly, due to unit displacement in global direction or in the global coordinate, what is the displacement along members TC or in my third elemental coordinate? If I want to know that, what I need to determine is what is this DD3. DD3. Okay, so here it will be 1 into cos of 30. 1 into cos of 30. So that comes out as 0.866 minus, again, because this member length will be shortened when you apply unit displacement in vertical direction, in vertically downward direction along the global coordinate. The member CD will get shortened over there. So for that purpose, negative sign has been assigned over here. Okay. Now coming to the second global coordinate, I'll apply unit displacement in the second global coordinate like this. This is my second global coordinate. A unit displacement has been applied here. Due to that, what will be the displacements in member AD member BD, member CD. If we find out that, that will give us the displacement in our elemental coordinates, because all our elemental coordinates are along the member AD, BD and CD. First elemental coordinate is along member AD, second elemental coordinate is along member BD, third elemental coordinate is along member CD. So unit displacement is given here in the global coordinate. Now again, I'll just consider each of the members over here. In member AD, the displacement will be directly 1, because what displacement you have given in global coordinate, it is along the member AD. It will be oriented along member AD. So in the first elemental coordinate, that is D1 star 1 will come out to be 1. It is extending, so it is taken positive here. So member AD is being pulled. It is elongating in length, so that is taken positive. Now second elemental for displacement, that is D2 star 1, D2 star 2, sorry. Okay, so here we have D1 star 2. The displacement in elemental coordinate 1 when unit displacement is applied in the global coordinate 2. So that is 2. That is the displacement along member AD. So it is coming out to be 1. So that is 1. Now second elemental coordinate, if you choose that one, this BD member, so this second elemental coordinate is along member BD. So I'll just extend this member, this one center line over here, and from this point I'll drop a perpendicular onto this second member. So if you determine this D2, that will represent the displacement in the member BD. So what I have here is, it is 1 into sine of 60. Okay, sine of 60, 1 into sine of 60, so that comes out as 0.866. So that will be the D2 star 2 displacement in the second elemental coordinate when unit displacement is applied in second global coordinate. So, coming to the third elemental coordinate, that is which is along member CD. So I'll calculate this D3. So that will tell me what will be the displacement in the third elemental coordinate, which is along member CD. It will be 1 sine 30. So that comes out as 0.5. So these are our elements of the second column. So D matrix can be now written by taking this values. So once we have this displacement transformation matrix, global stiffness matrix can be determined by this relation D transpose K star into D. So this is what I get here, the global stiffness matrix. The condition of equilibrium tells us P, net force in any coordinate, should be P into delta, force developed due to the displacement, first plus force developed due to the applied loads on the member. Here PL is 0. Directly I can rearrange this and put it in this form as K inverse into P. Delta, unknown displacements, can be determined by this relation K inverse into P. Okay, so on solving, you'll get delta 1 as 128 mm, delta 2 as 55.42 mm. Now to obtain the member forces. So member forces can be found, that is force in member AB, AD, BD and CD, F1, F2, F3. They can be found by using this relation K into D into delta. So if you multiply this, use this equation, you'll get the member forces. So here what we are getting is, force in member AD is 55.42 kilonewton. Force in member BD is minus 16, indicating it is compression. Force in member CD is minus 83.13 kilonewton. So these two are under compression, which are coming out to be negative. They are under compression. Okay, so we have got all the forces in this member using stiffness transformation method.